Hello, this is Professor Matt W. with another episode of Science Unboxed, where we discuss different concepts in quantum mechanics and in the field of science and break down ideas so that you can understand them. What we're going to work on today is finally connecting quantum mechanics to the field of chemistry. We've been waiting a long time for this serious connection, and this should start opening some old memories in maybe your high school or college chemistry class, certainly organic chemistry. Where did we leave off? Well, I just want to remind you we left off with the idea of momentum, which has to be greater than or equal to the Planck constant over 2 pi. So that's in the equation, that's the change in distance times the change in momentum, which is we can think of as a change in velocity, but it's a change in momentum because electrons and particles have mass, has to be greater than a very, very small number. We call the Planck constant over 2 pi. So that means basically as things get very, very small, this equation actually starts meaning something. For big objects like us, it doesn't mean that much. But for very small mass objects, it starts making some big differences in how we view the universe. And a couple of the ways is it creates an uncertainty principle where you can't know the exact position of a wave or a particle and also know its velocity at the same time. So as you know more about one, you know less about the other. But we're gonna go further back when we talked about waves. And what we've seen so far is that in the circular geometry, the symmetry of a system allows for two types of wave nodes to happen. Right? We went over kind of what a wave intrinsically is bound up by. It has boundary conditions that are determined by the geometry of the wave, which is whether it's a circular wave or if it's a transverse wave or a sinusoidal wave, like a perpendicular wave. And it's also bound by other factors. Because of the wave nature of particles, it's helpful to familiarize ourselves with how waves behave in various circumstances. This will help us immensely when we turn our attention to problems like quantum harmonic oscillators. That is how frequently they change, and the quantum structure of atoms, which is what this lecture is about. So what is a dimension? We use this term all the time, and I use it frequently. A dimension is any direction in which you can walk or you can jump. For example, I can move right to left, up and down, front or back. There's 3 different ways or dimensions I can move in so that we can say we live in a 3-dimensional space. So far, we've explored what standing wave modes can look like in a 1-dimensional geometry. Each time we put waves on a slinky, so if we have a slinky, we've been exploring what types of standing waves can form in a 1-dimensional system. The reason we've been doing that is because quantum mechanical waves also make standing wave shapes, but they do it in all 3 dimensions of space. You gotta start thinking in our 3 dimensions. Once we get into supersymmetry and string theory, we gotta start thinking in many more dimensions, 20 dimensions or 200 dimensions or 1,000 dimensions. Now, that can be a little bit difficult to visualize. So to help us get there, what I'd like to do is build up our thinking about standing wave shapes from the 1-dimensional case that we're familiar with waves with a slinky, to a 2-dimensional case of standing waves modes like on a drumhead, then all the way up to the 3-dimensional standing wave modes. And these will be the shape of modes that electrons take around an atom. First, let's remember that these wave modes look like what they look like in 1 dimension. We've already seen some key characteristics of standing wave modes on the slinky. When we see a standing wave mode, it has a regular, repeatable behavior, and each mode is distinct. The first mode on the slinky has only a hump, and the only places where the wave is not moving are at the very ends where it is tied down. The second mode has 2 humps and 1 more node in the middle, and this mode vibrates a lot more frequently than the first mode, so it has more energy. The third mode in 1 dimension has even more humps and nodes on it, and also moves a lot more quickly than the lower energy modes. Now, the resonant modes that waves take depend on the geometry that they're confined to. If we change what's called the boundary conditions of any wave system, then the shapes of the standing waves will change accordingly. We can make this demonstration on a slinky as well. So we've got our slinky again, and this time instead of having someone hold the other end of it like we usually do, the slinky stretches horizontally so it touches the ground and comes back up. We're going to hold it in only from the top and let the bottom go free. We're still in one dimension, but we've changed the boundary conditions because now one end is free and only one end is tied down. So now when we go to look at the resonant modes of this system, they're going to be similar to what we saw before, but because the boundary conditions have changed, they actually do have different overall shapes. For example, the first mode, and it's got a very slow motion and even slower than the first mode that we had when both ends of the slinky were tied down. And it's basically going to create almost like a circular pattern, right? With the second mode, there's a node in there now near the bottom, and it's going to look a little bit faster. And if I had a slinky here, you can see that, and I'm going to put some visualizations of that. In previous podcasts, we've noted some examples of wave modes that we encounter in everyday life. Maybe you're like me, you've been fascinated by watching the circular ripples that happen in a coffee cup when you put in, your sugar or your Splenda, or maybe you've thrown a rock into a pond that was all quiet before the rock hit it and watched the wave slowly circulate. In each case, the particular wave shape that happens depends on the geometry of the system and the boundary conditions. The boundary conditions are the things like where the edge of the system is and whether the wave is allowed to move at the edge of the system or not. Notice that the waves in your coffee cup have a different boundary condition from the waves that happen on a pond when you throw a rock on it. The different boundary conditions affect the shapes that the waves can take and how they behave, just like we have when we have the slinky. When we dropped the slinky, we didn't have someone else holding the slinky on the other side. That's a change in the boundary condition. So if you've ever jumped on a trampoline, then you have firsthand experience of the first mode that happens on a drumhead. But drums also create these wave patterns, right? In the first mode, the whole membrane moves up and at the same time passes back down through the middle, like when you jump on a trampoline, and then moves down at the same time. Only on a real drumhead, this motion happens really, really quickly, so it's hard to see. This type of motion on a drumhead produces the lowest frequency in the sound that you hear coming off the drum. Lower frequency modes have longer wavelengths, so this helps us understand why it is that larger drums have a lower sound, lower pitch, lower frequency. In a standard trap set, the bass drum has the lowest sounding note. If you've ever worn a sombrero, then you know what the second mode of a drumhead looks like. Here, the drumhead moves up and down in the middle, just like you'd expect, and it also moves up and down in a ring around the outside, and there's one note in the middle, where the wave is not moving. Because of the geometry, this mode makes a circle. If you remember that it's like what it's like to wear a sombrero, this is about what it looks like. So the sombrero hat has a ripple at the top and then has a frill at the bottom, and that note is at the top. And of course, we can keep on going like this into multiple sombrero-like shapes on top of each other. You probably already guessed that the next mode in this series has two nodes on the drumhead. They form concentric rings centered around the point in the center of the drumhead. Now, because these waves are happening in a two-dimensional surface, we can also make a completely different set of modes happen. In this mode, for example, places where the waves are vibrating the most are no longer in the very center of the drumhead. Rather, they're off to the side. And now the node that's happening, rather than being a great circle, this node where the wave is not moving, it forms a straight line that passes right through the center. This particular mode looks a little bit like a baseball cap with a bill turned up. So kind of like this. This is actually a shape that you can make with your hands by turning one hand facing up and the other down. The main feature of this series of modes is that the nodes, the places where the wave is not moving, form a straight line which passes through the center. Keeping that in mind, can you guess what the next standing wave shape is in this series must look like? Rather than having one line node which passes through the center, the next in the series of standing wave shapes will have two line nodes that pass through the center, and these line nodes are equally spaced around the drumhead, running north, south, east, and west. So now in this mode, at any given instant, the wave is making two crests and two troughs, and then those crests and troughs oscillate up and down. But the whole time that this motion is going on, the drumhead is never moving along the two line nodes that cross at the center of the drumhead. It's kind of like in this configuration, the drum is divided itself into northeast, southeast, southwest, and northwest. And those quadrants are the only places that move. And you can keep on going and add as many line nodes as you like. Each new line node also passes through the center. They're constrained to pass through the center because of the circular symmetry of the drumhead. So the next standing wave shape in this series will have one more line node. Now, if we think of how 3 line nodes should be arranged themselves, they look like an asterisk or a 6-pointed star that radiates out from the center of the drum. If you were to think about walking around a circle on the drum head during this mode, you would encounter 3 series of crests and 3 series of troughs. And there's a whole infinite series of these kinds of shapes modes on the drum head. Notice that one of the key features is that as you walk around the circle of the drum head, you have to come back to where you started. As you walk in a circle, you always pass by an integer number of crests that the wave is making. It just wouldn't work to put 2.5 or 2.25 crests around the drum, because then the wave wouldn't meet back up with itself. A very important concept here, especially when we start thinking about the shapes electrons can do in 3 dimensions, a very important concept is that the wave always has to meet back up with itself whenever you go in any loop in any direction. What we've seen so far is that in the circular geometry, the symmetry of the system allows 2 types of nodes to happen. The first type of node we encountered was the circular geometry, and the circular nodes are centered around the center of the drum. You can have as many circular nodes as you like, as long as they stay concentric. The second type of node we saw is a line node that passes straight through the center. These lines radiate from the center of the drum head, and again, we saw that you can have as many of these lines as you like, as long as they stay equidistant from each other. These line nodes form shapes like stars. These are the only 2 types of nodes that are allowed by the circular symmetry of the system. But you might have already guessed that there is a third type of standing wave mode that we can put on the drum. We can make this third type of wave shape by combining the 2 types of node that we've discovered already. What we're going to do next is to combine the first sombrero mode with the first mode that happened with a line node. That's the one that kind of looks like a baseball cap with its bill turned up. Now, the wave shapes that this will make will be constrained to have a single line node that runs through the center, in addition to a singular circular node, which is nowhere in the middle, but still concentric with the center of the drum. And here's what that looks like. It kind of looks like someone took 2 sombreros, flipping one upside down, and then sewed them together again. And if we keep going, adding more line nodes, adding more circular nodes, we can make some pretty crazy looking shapes. They start to kind of look like some sort of circular egg carton. Now that we have a feel for what standing wave modes look like in 1 dimension, that was the shapes we made with the slinky, and a feel for what they look like in 2 dimensions, these are the shapes that waves make on a drum head. Now we're ready to tackle what kind of shapes the waves of electrons make on the 3-dimensional area around the nucleus of an atom. Like any good game, there's some ground rules. The constraints are going to be the following. We want to know what are the natural wave shapes in this geometry. We saw in the case of the drumhead, the very center of the drumhead acts as like an anchor point. All the nodes that happen in that geometry either pass through the central point or were concentric to it. That role is going to be played by the nucleus of the atom now. We'll see that even in this more complicated case of a fully 3-dimensional geometry, any nodes that happen must either pass through the center of the nucleus or be concentric with it. That's going to be the first and most important rule of this game. But there are 2 other rules that govern the behavior of electron waves. Remember that the nucleus of the atom, there are protons and neutrons. The protons are positively charged while the neutrons have no charge. So overall, this means that the nucleus of an atom is positively charged. Because opposites attract, the negatively charged electrons are attracted to the nucleus. So there's this strong sense in which the electron wants to go to sit on top of the nucleus. We saw before that Heisenberg's uncertainty principle prevents that from happening, but that tendency is definitely still there. The fact that positive and negative charges are attracted to each other, that's an interaction energy, or sometimes you'll hear it called as potential energy. This is the second rule of the game. Electrons are, in fact, attracted to the nucleus. In addition to potential energy, particles have kinetic energy as well. Kinetic energy is the energy of motion, and the third rule in this game is played by kinetic energy. This one says that faster motion costs more energy. But the key to keep in mind is that when you are talking about waves, the waves that correspond to fast-moving particles have a lot of tiny wiggles in them at short wavelengths. So in fact, quantum mechanics, each time we add a node, that costs much more energy. And those are all the rules. The interplay of the kinetic energy with potential energy subject to the constraints of the standing waves modes in a three-dimensional geometry. All that sets the shapes of the waves that electrons make around an atomic nucleus. So at first I want you to think about the simplest atomic nucleus, which is a single proton. Once we put an electron with that will form a hydrogen atom. So what happens when we get the electron close to that proton? The electron feels the electrical attraction to the proton, and it kind of snuggles up to it. And then the wave shape of the electron settles into a standing wave mode, making a three-dimensional wave around the proton. Let's go ahead and think about what the lowest standing wave mode that the electron takes around the nucleus must look like. You must have already guessed that it basically looks like a big ball. Let's take a look at it. Just like we saw with the slinky in one dimension, and with the drumhead in two dimensions, there are no nodes in the lowest standing wave mode. If you had a chemistry class, you probably learned about atomic orbitals. Atomic orbitals are the states that electrons take in an atom. Those states amount to energy levels. There's a different state corresponding to each energy that an electron can have inside of an atom. And we already know that the shapes that quantum waves make tell us everything about the particle is doing, including telling us the energy of the particle. Each atomic orbital you learned about in a chemistry class corresponds to a different three-dimensional standing wave. You may remember them by their names. They're called things like the 1s state, the 2p state, and the 2s state, the 3d state, and so on. The first wave shape we looked at is the 1s state. That's the hydrogen atom. Of all the standing wave modes an electron can take around the nucleus of an atom, this is the lowest mode, and also is the lowest energy state. And we said already that one of the characteristics of this mode is that it has no nodes. There's no place where the wave is not moving, except infinitely far away from the nucleus. The shape of the wave tapers off quickly as you move away from the nucleus. It follows what's called an exponential fall-off, so it tapers off very quickly, getting closer and closer to zero as you move away from the nucleus. That is basically as good as zero once you get a few angstroms away from the nucleus. Why is there no node in this lowest energy state? This is actually a very general thing we find in quantum mechanical states. It's because having a node requires that the wave function wiggle more, and a wave that wiggles more has higher momentum, and higher momentum, something that's moving more, always has more kinetic energy. So the lowest energy state is a kind of compromise involving a low kinetic energy state, which is one with no nodes on it. But it still has to have the electron taking some shape where it hangs out close to the proton. The combination of this localizes the electron wave into a standing wave mode centered around the nucleus. And this wave shape, even though it's in three dimensions, it shares a lot of similarities with the lowest mode of the slinky and the lowest mode of the drumhead. Now, there's one last thing that I'd like to point out about the 1s state. Notice how in our visual rendering of the state that the color is changing with time. That is to represent the fact the wave is waving, just like the slinky went around in time. Just as how the drumhead moved up and down in time, the wave also needs to change in time. In the case of the electron, waves that I'm showing you, what's changing in time here is a number associated with every spot in the space, and that number is something we call a phase. The phase does change in time in a regular, repeatable way, and it periodically returns to the same value. For this reason, we can represent this by waving, the cycling of that phase, by constantly changing color that continually moves around the color wheel with some frequency and time. Let's see what the next model looks like. Now we see a ball in the middle surrounded by another ball. The other ball completely surrounds the middle one. They're both spherical and they're both centered on the nucleus of the atom. In your chemistry class, this is what is called the 2s state, and it's the second lowest energy state that the electron can take around the hydrogen atom. The standing wave shape has a node. The place where the wave is not moving is an infinitely thin spherical shell separating the inner ball from the outer ball. That represented in the animation by a dark circle where the inner ball and the outer ball meet. But keep in mind that it's not really a circle. It's actually a full three-dimensional spherical shell. Remember the types of nodes we could have on a drumhead. We saw that one type of mode on the drumhead has a circular mode where the wave is not moving, and that circle was centered on the middle of the drumhead. Here in this case, we have a spherical node and it's centered on the nucleus. Maybe you've already guessed what the third standing wave mode looks like in this series. We saw that with the sombrero series of models of modes on the drumhead, each higher mode added one more circular node concentric to the center. In the same way, the next mode on this series of three-dimensional standing waves modes will have two spherical nodes. Let's take a look. Now we have two fuzzy balls surrounding the middle ball, all concentric, all centered on the nucleus of the atom. That's what we call the 3s atomic orbital. This one has two spherical nodes, each node separating each of the three fuzzy balls. The nodes are all concentric with the nucleus. Every atomic orbital that's an S state looks something like this. There's a series of fuzzy balls separated by spherical nodes, all concentric with the nucleus, and the number of fuzzy balls corresponds to the numbers of states. The 1s state has one ball, the 2s state has two fuzzy balls, and the 3s state has three balls. You might be wondering about the size of these balls. They're all close to an angstrom, which is about a billionth the size of your hand. And as we add these spherical shells of nodes to the structure, the average distance between the nucleus and the electron increases a bit. So as you might imagine, the 3s state is larger than the 2s state, which is larger than the 1s state. So that was the first series of modes. The main characteristics of the S series of modes is that they form balls centered around the nucleus, and in between each layer, there is a spherical node separated one ball from the next. Let's switch now to thinking about a different series of standing wave shapes. Remember that for the drumhead, we had two types of nodes possible. One type of node had the circular symmetry of the drumhead itself. They were the circular nodes. The other type of node formed lines, and these lines intersected like a star at the center of the drumhead. Now let's turn back to our electrons wave in a three-dimensional space. So maybe you can already picture what the next set of modes should look like. Because we're talking about the shapes that three-dimensional standing waves take around the nucleus, the next type of node we need to consider, rather than being a line, that this type of node is going to be an entire plane that cuts space into two distinct regions, and each of these planar nodes is going to cut through the nucleus of the atom. So let's start by placing one planar node on the nucleus of the hydrogen atom and visualize what the type of standing wave mode looks like in that case. If you remember discussing these orbitals in a chemistry class, then you'll recognize that this is the 2p state. Now, when we look at these particular wave shape, the places where we see the brightest color are the places where the wave is wiggling the most. The wave never wiggles at all on the planar node that passes through the nucleus, and you can see that as you move away from the nucleus, the color fades into black. That's because as you move away from the center of the atom, the value of the wave itself drops like a rock and so on. So the only places that you're going to likely find this electron when you go look for it are along the color regions where we see it. Let's see what the next standing wave shape is in this series. Now we have two planes. They're both slicing through the nucleus, and in these planes, the wave does wiggle a lot, but the wave wiggles in each quadrant. We could think of it as northeast, southeast, southwest, and northwest. Another way to think of it is like we're taking an orange and cutting it into quarters. We could also think of cutting an orange into sixths or cutting it into eighths. We could even think of 10 slices of the orange. Each time we add another slice, the electron wave shape goes into a higher mode, and therefore we increase its energy. So we can see some definite similarities between the shapes of the standing wave and the modes take on a drumhead, and the shapes that electron waves make around the nucleus. Now you may have spotted a pattern in the types of nodes that were possible in our one-dimensional example of waves on a slinky, and then in our two-dimensional example of waves on a drumhead. In our one-dimensional waves on a slinky, there was only one type of node possible. Each of these nodes occupied a single point in space. When we looked at the drumhead modes, we were talking about waves that form in two dimensions of space, and in those two dimensions of space, we saw that there were two types of nodes possible. Some of the nodes were circular nodes, and they were always concentric with the center of the drum. The other types of nodes were line nodes, and they always intersected with the center of the drum. Now that we are thinking about the shapes that electron waves can make in a three-dimensional space, you can go ahead and congratulate yourself now. If you've thought there should be three different shapes, three different types of nodes happening in three dimensions. So far, in our three-dimensional standing waves, we've encountered nodes that are shaped like spheres and are always centered on the nucleus. Next, we've encountered nodes that are shaped like a plane, and each of these planes intersects with the nucleus. The third type of node that we'll encounter for three-dimensional wave shapes are nodes that are conical, which means that the places where the wave is not wiggling are shaped like the waffle cones at an ice cream shop. The pointed end of these conical nodes will always intersect the nucleus of the atom, and each cone will always have a mirror partner, as though the ice cream shop served your waffle cone standing straight up on a mirror. Let's look at an example. Here, the standing wave shape is set by two conical nodes that intersect at the origin. They're represented by the dotted lines. It's as though we were served a waffle ice cream cone that's standing upright on a mirror. And of course, you can add many more nodes like this, and the standing wave shapes get more intricate and they have higher energy levels. Here's a case with two sets of conical nodes, each all intersecting at the origin. This time it looks like we've been served a sharp waffle cone standing upright instead of a shallow waffle cone, all standing upright on a mirror. They're beautiful. I hope you enjoyed seeing what the shapes of these waves look like. In the next podcast, we'll see what the standing wave modes start to look like when we combine the three different types of nodes, and we'll see how these modes structure our periodic table of elements. So I just wanted to go over some of the many features that we discussed today. The different conditions, the different types of conditions that we have to think of with these different types of waves are the boundary conditions, okay, and also the geometry. So whether or not we see circular geometry or we see conical or we see other types of geometry. So we need to think about the border conditions and the geometry. We can see the quantization of the nodes and how they turn out to be and how that quantization relates to geometry by analogizing it to a gear. Electrons can have discrete amounts of energy. And if you ever used a gear shift, you have 1, 2, 3, 4 gear, but you can't go non-integer gears. So like if I'm in my car and I have a gear shift, most people have automatics, but if you maybe used a gear shifter in a motorcycle or an ATV or something like that, there isn't 1.5 gear. There isn't 2.5 gear. You have integer level gears. And just like that, electrons have discrete amount of energy. So they have to have discrete energy orbitals. And to understand this, think about what the gear looks like. You have to have a whole number of teeth around the gear, and they have to be evenly spaced. This is why you can only have discrete gears. In the next set of podcasts, I'm going to explain how this connects to chemistry in the periodic table, okay, and how we can move through the periodic table based on these SP, and we're going to find D states, or the S, the conical, the P, the combination states, and the D conical states that we see in the geometry of the periodic table and how each element really works. And I'm just going to summarize the standing wave shape that electrons take around the nucleus. They're going around and around the atom. They're going to depend on three things: the electrical attraction between the electron and the nucleus, the kinetic energy of the electron, and the constraints of the three-dimensional geometry. So again, electrical attraction, you got to think that the electrons are still attracted to the nucleus. Kinetic energy, that is how fast they're moving, and the energy, it takes more energy to be further away from the nucleus, and they're moving faster. And the constraints of the three-dimensional geometry. Once there is more than one electron in an atom, then you need to consider the spin of each electron, whether it's up or down. We haven't gotten to this. The Pauli exclusion principle that says that no two electrons can be in exactly the same space at the same time. That's a common feature of electrons, and the interactions in a whole class of subatomic particles, and the interaction between the electrons. These are the essential pieces of quantum physics that determine the structure of the periodic table of elements and set up the chemical building blocks of all matter. So this is the connection point of quantum mechanics. So why knowing quantum mechanics, the Heisenberg uncertainty principle, the idea of quanta, the idea that electrons can only have certain amounts of energy, how this connects to chemistry. And chemistry, of course, is going to be the building blocks of everything we see around us. Chemistry is really about the electrons and how electrons interact with each other. Understanding how we get to the point of where the electrons ultimately are around the nucleus has incredible implications for bonding, for creating molecules, and eventually creating organic structures. And that will be the focus of the next podcast. I hope this was an enlightening and helpful episode of Science Unboxed. And next lecture will be connecting it more to chemistry, where those electrons sit and why they sit, and what elements we can see in the periodic table with electrons are determines the behavior of an element. So until next time, stay curious, my friends.